Hi, everyone. So yeah, like Matthias mentioned, in this session, we want to disassemble Beam a little bit and gain some insight into what happens when you write your pipeline. We want to look at how the pipeline is translated also and finally executed by one of Beam's runners. A little bit of a disclaimer, to be frank, this is intended to be an interview, an overview, I mean, not an interview, but we are obviously not going to be covering all the details, but I'm really curious to hear your questions at the end of the talk or throughout the Beam Summit. And I'm also happy to expand on any of the things I'll cover in this talk. So please write down your question or post them in the chat. I'll be happy to answer them. So a little bit about myself, just a few words. I'm a software engineer and consultant. I've been using Flink and Beam for quite some years. I'm a PMC member and committer at both projects, and I worked at Viverica, the company which basically created Flink. And I also worked with Google and Lyft as a contractor, and I've been focusing on Beam portability and the Flink Runner. So I think I know what I'm talking about, but yeah, I'm still curious to give this talk. So what is Beam? This is not an introduction talk, but just for completeness. Well, Beam has like three characteristics, at least for me. Well, obviously it's for parallel and distributed data analytics, but it has these unique features of having a unified API, having multiple programming language that you can use for composing pipelines, and also you can choose your execution engine. So here's the typical slide we show. So yeah, you write using any languages. You have this pipeline, and then it's translated to the runner of your choice. But how does this work really? I mean, this is kind of a tricky thing to have all these SDKs and runners. So I wonder, or at least I wondered when I first got into Beam, how this would be possible if you have hit pipeline run. How then everything kicks off. So I'm gonna walk you through these 4 steps. Starting with the pipeline, then the runner, then deployment, and then finally execution. So let's start with the pipeline. And sometimes we refer to this internally as the runner API, but don't get confused by that. So let's look at what is a pipeline. Well, a pipeline is a series of transforms, which, well, it's composed of transforms, and transforms can take inputs, but they don't necessarily have to. So there's a special type of transform which doesn't take an input, but produces an output, a P collection. And then other transforms take that P collection as an input and produce other or multiple P collections. This is obviously like kind of a graph, and it can also be more complex, again, taking multiple inputs to transforms and yeah, branching off. So how does this look like in the API? Well, we create the pipeline. We bootstrap the first P collection using a transform which takes the pipeline as an input, so kind of a source transform then. And then we can produce a new P collection by applying a transform to the first P collection. And this goes on, and finally run it. So what is kind of important to understand when using Beam is that Beam is really composed of a few just a few primitive transforms, a set of primitive transforms. And these are listed here on the right side of the slide. So we have read, which is now deprecated, but you can still be used, is impulse, pardo, group by key, assign windows, and flatten. So we don't need to exactly know what these do, but we need to know that these are the primitive transforms, and everything else is kind of built with these. And these are called composite transforms. So composite transforms, they expand into primitive ones. For example, if you do a combine, then often you have a pardo, a group by key, and a pardo, which would be kind of like running a word count, where you have your words and input. You first assign like ones to them, you group by key, well, by word, and then you sum up the values. So that's composite transforms. And if we now take a look at the Runner API, which represents this pipeline, we first see a development in Beam that early days we had just this Java pipeline, and everything was in Java really. That was part of Beam. And then we introduced this Runner API I mentioned previously, which really is a universal structure for the pipeline that we just saw how it looks like. But how is it represented in the Runner API? And if you saw one of the previous talks, you already learned that this is written in protobuf, which doesn't really matter. But the cool thing about protobuf is that it's available in all these languages, Java, Go, and Python, and others. So if we take a look at how this actually looks in protobuf, we can see that this is really simple. And I just wanted to show you this. So protobuf has these messages, which is like just a structure to hold data. So, and you can see a pipeline is actually just components and the root transforms, which, I mean, you need to start somewhere, right? So these are actually the transforms which don't take an input. And then everything else is contained in the components. So if we take a look at the components, we can also see how they look like, and we can see components are just transforms, P collections. Well, that's not a big surprise. Window strategies. Well, if you use windowing, then these are also contained there. Then we have coders for transmitting data over the wire. We need to somehow turn them into bytes and convert them back. And we have environment, which are important because we want to have we support multiple languages, which might require a certain environment to execute, like a Python process or a Java JVM. So with that being said, let's dig a bit deeper. Let's look at the P collections and what they are composed of. So by the way, this is just a map because every transform has a name, and every P collection, of course, has a name. So it's always a map of P collection or transforms. So let's take a look at the P collection. The P collection just has a unique name, and it has a coder assigned. So we know how to decode and encode data of this P collection. And it also tells you, is it bounded or not? So we know we can optimize based on this information. And again, window strategy, we don't have to be concerned with this now. And yeah, so we saw the components, we saw the P collection, the transforms. No, we didn't actually see the transforms. Let's look at them now here. So again, transform just has a unique name to be able to identify it globally. And we have this function spec. And this determines like what kind of transform it is, like what kind of primitive or composite transforms it is. If it is a composite transform, it has these sub-transforms. So this is actually preserved in the pipeline. And we'll get later, we get to that later to see why that is useful. And then, of course, it has inputs and outputs. That's not surprising. And an environment, of course, if this is necessary. So let's take a look at the function spec. So this is still the same slide, but we're taking a closer look at the function spec. And we see that function spec is really a URN and a payload. So this is where basically we say, this is a Pardue or a group by key, and we can have a payload in case we want to store any additional data for that transform. So what transforms do we have? Well, we have the primitive transforms that I already showed you in an earlier slides, and you can see that represented in the protobuf message. So we have these primitives, and yeah, all of them are contained on the right side, listed on the right side. So Pardue, flatten, group by key, impulse, assign windows. And then we have also a set of deprecated primitives where the read is listed. And yeah, it goes on. We even list some of the composite transforms. Why would we do this? Well, it's because some runners can understand these composer transforms and translate them more efficiently than if they would just be expanded into primitive transforms. So there's combine per key reshuffle. For example, Flink has its own way to do reshuffle. There's no need to use the Beam expanded reshuffle. So the runner can directly translate these. And finally, let's take a look at just the Pardue payload. So the Pardue payload would be again would be a function spec, and this function spec would then, in this case here, would hold the code that the doFn in the Pardue actually is composed of. So a Python or Java code that you wrote in your doFn. And then we have side inputs, state, timers, anything you need to execute your Pardue. And finally, to conclude this pipeline section, let's also think ahead and let's realize that if you have the Pardue payload and with the function spec I just showed you, then I can actually put any kind of code in there. So I could also put Python, Java, or Go code in there. And this is what happens during creation of the pipeline by talking to the expansion service. So if we have an external transform, then this gets expanded, and for example, the Java code gets stored in the otherwise Python pipeline definition. Okay. So that brings us to step 2, the runner. So I'm using the Flink Runner here as an example, but really we could use any runner. But just to illustrate how this works, I'm using Flink. So we have a bit of a dualism going on in the Flink Runner, because Flink has a batch and a streaming API. So we already need to support both cases. And so depending on whether we saw earlier that the transform has the indication, is it bounded or not, so we know whether to use batch or streaming mode. And also we have this classic mode and the portable mode, which I will now go over. So we have like 4 translators. Doesn't matter unless you're working on Beam, but I thought it would be interesting to mention. So let's start with the classic mode, which was just Java, and then we will see how the portable mode is just an extension of that. So how does it work? Well, we have the Beam pipeline in protobuf, and we have the translators, which are defined in the runner, and then we end up with a Flink job, or a data flow job, or any other runner's job. So I guess one of the most interesting, or the first steps that we need to solve, is thinking about coders. When we pass data to Flink, Flink has its type system and knows has its own serializers and knows how to make sense of that data, how to serialize, deserialize it. Beam has a similar concept called coders. So in order to translate Beam coders, we actually create a special coder type information for Flink, which then if Flink asks for the serializer, it returns this coder type serializer, which is really just calling the Beam coder. So that's fairly easy. It's just like a kind of wrapper. And similarly, it works for the retransform, which is now deprecated. But in the old times, we had bounded and unbounded sources. So in order to match, to wrap these and to support these, in batch we have the source input format, which corresponds to Flink's concept. And in streaming we have the unbounded source wrapper. And this takes care of the splitting, the watermarks, the checkpointing. Yeah, and we even have an adapter to convert bounded sources in streaming, so we can use them in streaming mode and don't have to use batch if we have a bounded source. So, and basically this, I'm just going to continue here. I'm not going to go over all the details, but when we look at Pardue, again, we have the side inputs, side outputs, state timers, and we have basically a batch way and a streaming way to do things. And fortunately, all these concepts somehow, although they're slightly different, are mappable to Flink concepts. but it's not always like one-to-one. We often have to introduce another like compatibility layer, let's say. So in streaming, we have the doFn operator, and that does checkpointing and buffering of data, our watermark emission state and timers. Fortunately, Flink supports all of these capabilities already. And Beam is really helpful here because when it comes to windowing and triggering and garbage collection, Beam provides an interface for that called a doFn runner. And that doFn runner is available in different variations. So if you have, for example, to support garbage collection and timers and so on. So side inputs, for example, how are they translated? They are kind of unique to Beam. Flink doesn't have this feature. So what a side input is that you broadcast all the data of a P collection to all parallel instances of a transform. And then you kind of need to wait until that side put is ready, until you process your main input. And we have this functionality in Flink using broadcast stream and connecting this, but it requires a little bit of work to make this work. Fortunately, we have extracted this in the utility so all the runners can make use of it. This is the simple pushback side input doFn runner, really trying to maximize the class name length there. Side inputs, again, Flink didn't natively support them in streaming, but now actually does. In batch, it doesn't support it, so we wrap everything in this raw union value and tag it so we can later select which elements we want from the stream using a filter operation. And I already mentioned state and timers. They're stored in Flink's native interface, which is really convenient because it means that it's automatically checkpointed, and window computation and everything else is done using timers. We only have these available in streaming though. So what we do here is that we have for batch we have a special in-memory state internals and timer internals, which we can use instead. So Beam provides some good utility there. So finally, group by key, of course, groups by key and window. So that's a bit different because in Flink we would assign windows sort of lazily when we use a window operation. In Beam, you could always assign windows. Like when you have an element, you can just assign a window to it. And fortunately, we have this utility called reduceFn runner, which basically does all the logic which in Flink a window operator would do. But because Beam has its own windowing and triggering logic, we need to use that utility. And I mentioned windowing, so when we assign windows in Beam, they are assigned eagerly, and Flink lazily. The way window assignment works is that we wrap the value that we have, the data you have, inside a windowed value, which then holds additionally a window information. So, and this is just like if we have like hello, you would just say like interval window 0 to 10, and then include that hello there. But important to notice that an element can actually be part of multiple windows. For example, in the case of sliding windows, where we have where the timestamp of an element can be included in multiple windows. Yeah, I forgot to include, actually, there's also timestamp, of course, associated with the element. So flattened, finally, is just a union of P collections, which can be fairly easily translated also to Flink concepts. And finally, composite transforms. For Flink, we translate the combine directly because we have this possibility to use a local combine. I'm not going to go into the details. Otherwise, we use the Beam functionality in the data stream API. And yeah, reshuffle is also natively supported by Flink. So let's take a look at the portable runner, which allows you to run multiple languages. And I forgot to mention that, well, intentionally, that we also have the execution layer, which is called the Fun API. And if we look at this layer, we will see that in terms of the transforms, when we execute in portable mode, everything looks kind of similar. We don't have the read anymore. We have impulse plus splittable doFn, which, yeah, is just a technical detail. But other than that, it looks pretty much similar. What is an impulse? Well, impulse is actually just an empty byte array. It's just a trigger to tell a transform to kick off the execution, which was previously done with this read transform. Yeah, of course, you must only be emitted once and be checkpointed. So finally, let's take a look at pipeline fusion. So if we were to just use Pardue operations, like we saw here, if we had a lot of them with different languages, it would be really inefficient to bring up like a Python process for every Pardue code. But in order to optimize that, we use pipeline fusion. So we can actually include multiple of these functions in the same environment. And this is called an executable stage. So in an executable stage, we provide the input for a series of fused transforms. And that way we optimize and save processing power. How does it look like in the Runner API? Well, we have the executable stage payload, and there we can see the environment and the wire coder, the input, and the transforms that are inside. And we can actually have like multiple transforms receiving the same input and producing outputs. So that's pretty neat. And yeah, one thing to quickly mention here is that we can have cross-language pipelines. So we can have in a Python job, we can use, for example, the Kafka consumer from Java, which is really neat. But one thing to keep in mind here is that if we use only Java, only Python or Go, basically we don't need to be concerned about coders. I can write my own coder, and as long as I just use Java, it will be understood, because my other function that I have at the end of my pipeline still uses the same Java coder and everything is okay. But if we actually start mixing Python and Java code or Go and Java code, then we have a problem, because suddenly we might send data from Python to Java, and Java doesn't understand some Python pickle function decoder. So we need a way to have a standardized interface there, and this is called standard coders. And if we look inside the protobuf, again, we can see a set of coders defined here: byte coder, string coder, integer, double, like what you would expect. And finally, also schema coder, which is a very flexible way to combine all of these and to build new types, which we have more talks going on in the next days. So let's go to the almost final step, the deployment. In the classic architecture, we had a very simple model. We had the SDK, which produced a pipeline. The runner would kind of submit it against a Flink cluster, or we would build an Uber jar, and yeah, everybody was happy. But it was simpler, but it was also not flexible enough, because what if we wanted to run these executable stages which contain Python, Java code? Well, it gets a bit more tricky. First of all, we need to be concerned about staging the artifacts that are necessary. If I use a Python pipeline, I might have like pip install a library, and I want that to be available at runtime. So that's what the job API, the artifact, well, the job API submits the job, but the artifact API then stages the necessary artifacts. Then the whole thing gets deployed to Flink, and yeah, in the next step, this environment factory actually creates the SDK harnesses which run the Python, Java, or whatever code, and they communicate through the Flink job, the Flink executable stage, which is really the Beam executable stage, through the Fun API. So what is an SDK harness? Well, an SDK harness runs in either a Docker container, in a dedicated process, or in an externally managed worker pool. And can also run embedded in the case of Java. Yeah, so, and we added just recently a new mode called the loopback mode, which even further simplifies the deployment process by just locally starting a processing unit. But yeah, that's for testing and development. So finally, let's get to the execution part. So this is kind of the complete picture here. We have these multiple Python transforms fused together, running in the executable stage, in the environment, which communicates with the executable stage. And the executable stage handles all the input, output that the SDK harness produces, as well as timers, state, and so on. Then also we have the expansion service, which is there in case we do use Java, for instance, in a Python pipeline, some non-native language to the SDK. So here in this case, Java inside the Python pipeline. And to finally conclude this talk, I want to take a look at the Fun API itself. So what does happen there? I mentioned that I mentioned state and timers already, but basically you have the executable stages on the runner side, and you have these services running. And when the runner brings up the executable stage, it says, hey, start this environment, and the environment connects back to the runner. And you can see here, you can see under connect in the middle. I can't really point. Or can I point? No. So when the SDK harness has registered, the runner can then start registering a process bundle descriptor. The process bundle descriptor is like a stripped down version of the pipeline to just give the SDK harness enough information to execute transforms, or an executable stage essentially, which is a set of transforms. And this is really cool because in that sense, the SDK harness is stateless. So you can just start up a new harness, and that will register and receive the process bundle descriptor, and then receive any bundle requests. So again, this also covers, the Fun API also covers data and metrics and progress and artifacts, logging. Logging is very important if you want, so you know what is going on inside the process. And if we finally look one more time to what the process bundle descriptor is, we can see it has an ID, it has transforms, P collections, and so on. So it's basically a stripped down version, or an isolated part of that pipeline graph, which we saw earlier. So I mentioned bundles. Bundles are a Beam concept, and they're kind of nice idea because they allow you to balance latency and throughput. So basically, a bundle has a size, and if the bundle is composed of more elements or less, and that can be determined by fixed element count or a timeout for that bundle, you can balance latency and throughput if you allow If you do smaller bundles, you have lower latency. If you do bigger bundles, you have higher throughput. You can't have both, of course, but that's a nice way to tune your pipeline. So this is the complete picture that should give you an overview of what happens when you run your Beam pipeline. I'm really curious to speak with you and learn about what questions you have. This is quite ambitious to cover in half an hour, I guess, and there are many more details, I'm sure, but yeah, I'm just looking forward to your questions. So if you have more questions, ask me. Also, you can go on the website, register on the mailing list, which is really helpful. Also, check out the next Beam events, and of course, attend this one. And yeah, reach out to me if you want via email also or Twitter. And with that being said, I'm happy to hear your questions and looking forward to the next talks. All right, thanks.
Awesome, Max. Thanks a lot. That lifted some of the mystery of the whole Beam pipeline lifecycle for myself. So very interesting. We have a few questions from the audience. Some of them I see were already answered in the Slack channel, but just to reiterate for the whole audience, here we go. What is Purdue an abbreviation of?
Well, PADU stands for. Is this a quiz? No. PADU stands for parallel do with n. So and well, a do fn is, I guess, something, a function where you do something. Yeah.
Okay, perfect.
So
Let
this
me
is just for context. This is a do event is basically where you write all your business logic in. So this is where you receive your input and you can manipulate it, output it. Yeah.
Second question from the audience is a question about P transforms. And the question is a P transform essentially component in the protobuf message?
Yes, the p-transform is a central component in the protobuf message. I can just quickly try to show this again. If we go back here, God, too many slides. Yeah, so if we see here, we have this p-transform message, and right, and in this function spec, you would basically then have your like specify what kind of p-transform it is, like a Pardo or a group by key. Hope that answers the question.
Let's move on to the third question then. Why are states not part of the process context? And is there any design thinking in that?
State not part of a process context. That's an interesting question. That's a really good question. It's true. It's not part of this. Well, the Java process context. I think you're referring to that one. I think there was a design decision back then to not break backwards compatibility, I suppose, because user state was added later in Beam. Before initially we didn't have it for user support. So I think, yeah, this is the reason. And there's actually a new feature called timer or no, timer families. Well, there's also the option to dynamically add user state and not define it upfront. But I think that's still under development. At least for timers, it's possible.
Okay, cool.
So maybe
I, thi- I think a last question that would be, or a question that also has been bugging me at the start of learning Beam was So let's assume I make a Beam pipeline and I submit it to a Flink cluster or to a Spark cluster. When my code arrives in the Beam, when my code arrives in the cluster, does the Spark cluster actually know this is written in Beam, or is it just a plain Spark or Flink pipeline when it arrives?
That's a good question. Yeah, so Flink or Spark doesn't strictly know. I mean, it could detect it somehow, but it doesn't know it's a Beam job. It's just that Beam and Spark and Flink have these APIs which can be extended to include custom transforms or custom operators. So this operator is basically what we call transform in Beam. Doesn't matter, same thing. And we sort of, well, I wouldn't say abuse, but we integrate the APIs of Beam and of Spark and Flink to integrate the Beam code we need. Sometimes this can be, if in the case of, let's say, a timer or so, or state, this can be more or less directly mapped. Sometimes when we evaluate windows and triggers, which Beam has its own interface for, then we need to basically plug in the Beam functionality in the Flink and Spark interface. So it's a bit like the concepts are similar, but it's just that you need to plug it in there, let's say.
And by that time, we're already deep in the bowels of these different engines, I guess.
Yeah, of course.
Okay, cool. I think okay. There's one more question that just came in. The question is: are you going to support Spark Rapids API?
Hmm, I if I'm not familiar with this new API, to be honest, but I don't see a reason why we wouldn't support it. I'm not working on the Spark Runner actively, but I'll probably ask Ismail, for example, about the Rapids API and if he would be looking into it.
Yeah, I think this is maybe a good one to discuss on the Slack channel as well. I think there's plenty of people that have experience with Spark there, so maybe this is one we can take to Slack for further discussion. Then,
Awesome.
cool.
Thanks,
Thank you
Matthias.
very much, Max. And I think we're ready for the next talk. Then,
All right. Take care.
bye bye.